Alright, so what we're going to do is look at the exact same rate of change limit definition we've been talking about. However, now we change its title from rate of change or slope of the tangent line to the definition of the derivative. The key part of that statement is this is the definition. There will be times that a problem says, use the definition of the derivative, which means you can't use the quote-unquote cheat way, which is called the power rule, which is what we're going to talk about next week. The definition of the derivative means you must use the limit as h approaches 0. We have some facts about the derivative that we need to know now. So the derivative itself is simply called f prime. So f prime is the shorthand way for writing the derivative. This is how you will see it more often than not. The domain of f prime is the set of points in the domain of f. So that's a key piece of information. The domain of f prime is the same as the domain of f. There are times where the domain of f prime will be shrunk. If f prime exists, then we say that f has a derivative at x, or that f is differentiable. F is differentiable is another way of saying the derivative again. Lots of words, lots of meanings. A differentiable function is a function that is differentiable at every point of its domain. So the directions now may say differentiate using the definition of the derivative for f of x equals x cubed. Does anybody remember Pascal's triangle?
No.
So Pascal's triangle is a way of taking squared functions, cubed functions to the fourth, as long as they're missing their value on the front, you can use the triangle. If not, you have to actually start squaring and cubing them. But Pascal's triangle says, okay, if the top is 1, the next two sides are 1 to 1. The next one, you say, okay, 1 stay on the outside. Now I add to get my middle. So my middle is going to be 2.
I've seen Pascal's triangle.
This line right here represents the coefficients on x plus y squared. So it'd be 1x squared, 2xy, y squared. The 1 stay on the outside. 1 plus 2 is? 2 plus 1 is? This represents the coefficients of x plus y cubed.
This is insane. Now, can you do
1 stay on the outside. There's a trick for if they have numbers, yes. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. This would be x plus y to the 4th. So it would be x to the 4th, 4x cubed y, 6x squared y squared, 4xy cubed, 1y to the 4th. Each of these have to have exponents that sum to 4. So if you think about when you do this, I said it's 1x squared, right? So x squared sums to 2. This is 2xy. The exponents of x and y sum to 1 is y squared, sum to. Anytime you're actually ever factoring something out with FOIL, but not with FOIL because this would work with FOIL. But anytime you're factoring out the pieces of the individual parts, they always should sum to the highest power that you're factoring out to. So like this would be 1x cubed. Then the x decreases by 1, the y goes up by 1. So it's 3x squared y. Well, x squared and y sum to. This is 3xy squared. They sum to 3, 1, y cubed. There is a rule for if there are numbers on the x and y's. You can Google Pascal's triangle, and it gets a little bit more complicated because the coefficients have to also get raised to the powers in that same way. So if this was like 2x plus y cubed, then we said the first one, this term is 1, and then it's 2x cubed, so you have to cube the 2. And then the middle term is 3, it would be 2x squared y. So like this whole term would be squared. And then the next one would be 3, and it would be 2x y squared, and then it would be 1 y cubed. So the Pascal numbers stay, and then the terms decrease. So it goes 3, 2, 1, 0, and then this goes 3, 2, 1, 0. Do you see it?
Yeah.
So does that answer the question you were going to ask? It still works. It's just that you have to do the powers with the numbers also.
Ooh. That's like insane.
That's Pascal's triangle.
That's just I've never heard that in my life.
That's kind of.
Because it wouldn't. You haven't heard it because surely, except for maybe Lester and Trey, you didn't hit these higher powered values, and you didn't have that much with polynomials.
Taking cubes would be so much easier.
I told you how to do it now. You won't, because, again, here's a prime example. It's the limit as h approaches 0 of x plus h cubed minus x cubed all over h. So now I have less to think about. I don't have to square x plus h, then distribute x plus h again. I can simply apply Pascal's triangle, which says the x's are going to go up. Well, I guess it doesn't matter. X's are going to go down, h's are going to go up, and the coefficients are 1, 3, 3, 1. So it's x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. I've just saved you probably 3 minutes of factoring.
Yeah, that part kind of takes a.
Limit as h approaches 0. What happens? My cubes cancel, right? So we're left with 3x squared h plus 3xh squared plus h cubed all over h. What's the common theme of everything in the numerator? So as long as each part has an h, we can say goodbye to 1 from each piece. Thus giving the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now, since there's no h in the denominator, we're okay to take our limit. The last two terms zero out. And we get 3x squared.
I'm so curious about power rule now. Like, that's just
Google
crazy.
Pascal's triangle. It is really cool to see it in action.
I had
There's
it
a
up,
really cool video on Khan Academy too, if you watch it on there.
There was some sweepstakes for like this video card, and you had to like solve a riddle with Pascal's triangle. It was so weird. That's just how I kind of know about it. It was hard. I couldn't figure it out.
So now, like, you actually know the application.
I know what it means now.
Yeah. All right, you're going to see the definition of the derivative defined as the derivative at a point as well. So this is where you have f prime of a, and this is why I'm sorry, like when I started to do the one problem earlier, I used x. It's because in my mind I was jumping to today's lesson because I had already looked at my notes. So I apologize, that's why the homework problem I started to do, I was messing you up a little bit. So you can actually change your limit to be the limit as x approaches a. What is this right here called? What do we define this as?
Rate of change.
Or
Secant?
slope of the secant, yeah.
Make sure that there's
Rochelle Burgess and Emma Lyle, please come to the office. Rochelle Burgess and Emma Lyle, please come to the office.
Ooh, I just saw the NCB.
So you know where we're headed.
No,
You really didn't
not
see it.
really. I did see it, but I just didn't.
So, I mean, once again, the process, the idea, the concept is the same. The limit as h approaches 0. We're going to start for part at the beginning of the general, and then we'll look at them at specific points. So you have h approaches 0. Instead of x plus h now, you could write it as a plus h. So it'd be a plus h squared minus 8a plus h plus 9. Here's where you have to really watch your signs. It is minus all of this. And a lot of us tend to just put it on the x squared term and forget about the 8 and the 9. But this aspect is in parentheses in a sense. So this is really like a squared minus 8a plus 9. So that negative between them is distributing to all three pieces inside. So you have the limit as h approaches 0. Let's use that Pascal's triangle. So this is going to go 1, 2, 1. So it's a squared plus 2ah plus h squared. I'm going to distribute my negative 8 to a and h. And I'm going to distribute my negative to everything in the parentheses. All over h. Let's clean it up. What cancels?
It's 9s.
We're canceling yellow today.
8a.
So a squared and negative 8a, right? Start slow. Go at the beginning so you don't miss anything. Nothing cancels with ah. Nothing cancels with h squared. Nothing cancels. Oh wait.
Oh, yes, it do.
Negative 8 is positive 8.
And the 9.
This doesn't cancel, but the 9s cancel.
I'm so hungry. And I eat at 6.
You can, this is Moana, has like tons of Pop-Tarts and like stuff for sale for TFN. She went to Sam's Club yesterday and restocked. So I'll give you some time at the end of the fourth to go over and buy something.
Oh,
If you have like a dollar, do you have a dollar or two in
cash?
cash? Yeah, then you can go over and buy stuff.
I'm not gonna
Although you're not
didn't
dying.
know about that.
No. Cancel out your h's, right? So you got the limit as h approaches 0. So goodbye h here, 1 there, 1 here, that 1 there. So you're left with 2a plus h minus 8. So your h zeroes out when you take your limit, and you're left with 2a minus 8. You can now plug in any value for a, find the slope of the tangent, and write an equation of the tangent. Okay, square root. Those are your favorites. So you have the square root of a plus h minus the square root of a all over h. Minute you see square roots, you see a negative between them, you think
Complex
conjugate, right?
I like it.
So you got square root of a plus h plus the square root of a all over square root of a plus h plus the square root of a. So you got limit as h approaches 0 of a plus h minus a. So now we got a double square root all over h. Are you okay back there? A plus h.
Yeah.
Okay, now. Goodbye A's, goodbye H. What's the sign on the H? That's really important. What's the sign on the H? The sign is a positive. So that means you're going to have a plus 1 in your numerator. Then you got square root A plus H plus square root A. Plug in 0 for H. You got root A plus root A. Root A plus root A, same bases under the square root, so you can add their coefficients. 1 over 2 square roots of A.
Alright. What are we moving on to?
Hold on. You need to, yeah, she took my paper. Yeah, hold she is getting something from before.
It's just,
At least plugging in the A plus H's.
Wait, where are we going? Oh, it's the next. Oh, we got an extra page in between. Okay. Yeah, I have the one-sided derivative next.
No, example 3, the one with the chart at the bottom of it is where we're going next. So, one more time. Limit as h approaches 0. You see now why I gave you the worksheet I gave you yesterday. Like, this isn't going away, at least not anytime soon. So you have 1 over 1 plus a plus h squared minus 1 over 1 plus a squared all over h. I would find my common denominator before I FOIL. I would find the common denominator before I FOIL out that a plus h squared. So what that means is I would turn this to limit as h approaches 0 of 1 plus a squared minus 1 plus a plus h squared all over h 1 plus a squared 1 plus a plus h squared. Be really cautious, really watch your parentheses, and really pay attention to how you write it. Now, let's get into some gross algebra. So I have 1 plus a squared, right? Minus, I'd keep that parenthesis for now, because you got to FOIL the a plus h. So you have 1 plus a squared plus 2ah plus h squared. Do not FOIL or factor your denominator out yet. Keep it as is. Distribute some negatives. Cancel some numerator. So 1 1, a squared, a squared. Can we cancel an H? You can GCF it out. Take our limit, so that's zeros, this zeros, so I get negative 2a over 1 plus a squared, 1 plus a squared. That's why I told you you have to factor it or FOIL it out, because a plus 0 eventually is just going to become a squared. Those are the same. We'll come back and look at this when we learn quotient rule. All right. We have lots and lots of notation for calc things. I don't know why I wrote that on line for you. What's the one that's right over top? So y prime, we say this as y prime. So the first one is how you say it. dy dx is read as the derivative of y with respect to, that's what WRT stands for, with respect to x. df dx is the derivative of x, or the derivative of f rather, with respect to x. And the bottom one is the derivative of f of x with respect to x. The second column is why we use that notation, but also maybe why we don't use that notation. Y prime is the shortest one to write. However, we do not know the variable that we are deriving. Any of the ones that have WRTX, tell me the variable I am deriving it with. So when that dx is in the denominator, that tells me the variable I'm deriving it with. So dy dx names both variables where the d stands for derivative. This is also Leibniz notation.
So if you have like, you have an equation that was like y equals x plus z, then if you like the derivative of y with respect to z, you just plug in x plus a plus h equals z.
Repeat again what your fraction would be.
Fraction? Oh, derivative of y with respect to the derivative of z.
Okay, it wouldn't be derivative of z, it would be derivative of y with respect to z. So that would be dy dz.
So then you plug in like a plus h and it's just z, and then it's x.
Yeah.
You have like
We don't use this notation with the limits. No. This is building into the real derivative. Oh, Lebnoitz. I know, I got one above the T, so then I made another one. And now it looks like a double dot. And my eraser isn't small enough to like erase in there.
Use the white. Is that like?
yeah, you can use white.
True. Alright, df x emphasizes function name. F of x with respect to x emphasizes differentiation of f. Honestly, these two are the most popular notations you will see. The top two are the ones you're going to see the most.
Will all of these be like tested?
I mean, they can write, there's so many ways to write things, and that's what you're going to see as we continue through functions and problems. What we're going to do from here is we're actually going to look at the rates of change with respect to graphs. So what we're going to do now is look at the rates of change with respect to graphs. Why don't we, like, I would put it where you will never lose it, or you're going to want to write it on a note card. You're going to want this chart forever.
Can you just like read down the abbreviations?
Increasing, decreasing, extrema. Concave up, concave down. Point of inflection. Column 2. Yes. Positive, negative, 0. That 0 can also kind of be a DNE, and we're going to talk about that. Increase. Here's something really cool too. Ready? What are the first 3 lines here? Increase.
Extrema.
Oh, look what repeats.
What? No way.
What are the first 3 lines here? Look what repeats.
Wait.
These 3
Are those 3
repeat there.
negatives?
These 3 repeat. It's really not, because the actual, if the original is increasing, the derivative is positive. So this is like the original, and this is like the derivative. So the property repeats itself. Inflection, which means it changes from like a smile to a frown. And an extrema is a min or a max. It's just that means both. Yes, dear.
For F double prime, whatever
Yes.
that is it 3 negatives? Is that 3 negatives?
2.
Oh. So
Oh, these negatives are like, nothing happens with the second derivative here. They're like blank. That's why they're like long. Yeah, they're like blanks or X's or like they're not. That does not mean negative. Sorry, that does not mean negative.
Okay, that's why I was like, why would the acceleration be like?
I'm like, why? It doesn't make any pattern.
They're just blank. There's nothing there. Whatever happens on the original, nothing can happen on the second derivative with increasing and positive. Sorry.
That's why we ask questions.
I never realized that with negative. So we're going to take this idea and use it to help us graph the derivative from an original function.
This pumpkin spice stuff is good. I've never had it.
Oh, it's delightful.
It's not bad.
All right. So if the original function is increasing, so from A to C, we are increasing, right? So f is increasing from A to C. What does that mean the derivative is doing now? So if f is increasing, f prime is positive from A to C. I'm not rewriting all that. If f is decreasing from C to F, then the derivative is what? Perfect. So f prime is negative from C to F. From A to about D, this graph is what? So that means F is concave down from A to D. So F prime is what when it is concave down? And F double prime is what? If F prime is decreasing, F double prime is
Negative.
Positive.
negative.
I think I see increasing.
That means D is probably what? D is what we call a POI. It is a point of inflection. If the slope of a function is 0, that's like saying the velocity is 0. So what's happening on the graph? It is doing what? It's the extreme. So if they tell you right here the slope is 0, these points, remember slope is the rate of change, which is the derivative. So all of these slopes actually represent the derivative value. So maybe give yourself a little note. Slope represents derivative value, aka slope is our, and again I'm doing this in green because green is always the derivative. So if the derivative is 0, the original is in, so f prime is 0 at C and F. So what's happening on my original then? If this derivative is 0, the original is a extra. F is an extra. So much information from a tiny little graph. And there's so much more we can actually pull from this than what I'm giving you. Let's try to take everything we have in green and draw the graph of that. So again, we know the slopes, right? So they can help us get the points on the derivative. So at A, the slope is 4. So that means the point is 0, 4 on the derivative. If A has a slope of 4, that 4 represents the value of the derivative. So that means on this graph here, I have the point 0, 4. The slope at point B was 1. So B appears to be roughly at like 2. No, C is at 2, so B is at 1 maybe. So we have the point 1, comma 1. 2 was what? 0. Point D is at 3, which is -1. Point E is at 5, which was also -1. Point F is back at 0. And that was at 6. What do you think is probably happening at 4? So if you go back to your graph, is that going to be a positive or a negative value? Negative, and that's pretty steep, right? So it's probably a little less than -1, so it's maybe like a slope of -2. So I'd say it's like maybe right here. Think about what does that graph look like? What does it look like? A parabola, which is known as a
First one should be cubic.
oh yeah, it kind of looks like a cubic, right?
Yeah.
Goes up, down, back up again. Cubics are odd. It's going in opposite directions. So isn't it safe to say that the derivative decreases by 1 for the power? So we have a cubic and we get a quadratic. If I made the derivative of this one, it would probably be
Linear.
there you go. And then linear would turn to
Online.
constant. Awesome. Sometimes when we look at limits, we have to look at one-sided limits, right? The same is true for derivatives. Sometimes we have to look at one-sided derivatives. So what happens is we might have to listen or look at the slope of this only from the positive or the slope of this only from the negative. Okay. So you don't really have to write down a lot. I was just kind of giving you a minute to read through that, maybe comprehend what was happening. So the most common application of left and right-hand derivatives is going to be piecewise functions. Because a piecewise is coming in from the left and coming in from the right, and they needed a point. But the derivative from the left is probably not going to equal the derivative from the right. An easy example of that would be an absolute value, right? So absolute value from the left is going to have a derivative that is negative, right? What's the slope of this line? It's going to be negative because the original is decreasing, therefore derivative is negative. From the right, this is going to be increasing, therefore derivative is positive. So the left-hand limit versus the right-hand limit at 0 are going to be different. Functions that have very sharp points are not differentiable at that sharp point. So that's why we need to use left and right hand derivatives, because they're not differentiable at that sharp point. So here, we have two entirely different functions meeting at a point. If I were to graph this quickly in my mind, what I see is on top, I have x squared. So I have this quadratic, and on the bottom I have 2x, So I have this linear, and they're going to come in and they're going to meet, and they're not really going to match up very nicely, right? This is what that one bonus multiple choice was asking you. It was asking you to make the e of x and that other function smooth and soft like this. But some of the points would have made it like that, and that. And that's what you had to get to. You had to make it smoother than this. So what we do is for this type of function, we look at the left hand and we look at the right hand. So what you want to do is you're going to look at the limit on top. Oh, did I flip-flop that one? Okay. You knew what I was drawing. I kind of wonder if Sam was giving me this weird look. There you go. All better. I realized once I started to write my limit. There you go. So we have the limit as h approaches 0. This is going to be from the left. So how are we going to write it out? Okay, you can do x plus h squared minus x squared all over h. X squared plus 2xh plus h squared minus x squared all over h. X's cancel, x squareds rather cancel, and h cancels. So the derivative coming in from the left is 2x. At the point x equals 0, what would that slope be then? So the left-hand derivative at 0. So now looking at x equals 0, my value becomes 2 times 0, which is 0. Because x is kind of like my a. Or a is 0, however you want to think of it. Let's look at the limit from the right. So now I have 2 times x plus h minus 2x all over h. And that means that, again, we talked about it, the derivative of a linear function will become a constant. So that means the derivative of this orange function would always be 2. The derivative of the purple function would always be 2x. So that meant whatever your x was, the derivative was. So it would kind of look like this. And don't think it's not intentional with x squared's derivative is 2x for this piece was. Derivative of 2x is x was 2. And then it would be, what would be the derivative of 2? 0.
So those lines prove that constant line and then.
All right, we are done. Don't worry about the example on the back. That was there when I used to teach business calc.